Lydia Fayard. Okay, did I do that? Okay, somebody with even
Almost
complicated than me. And she's going to give us an experimental overview of the scalar boson. Politically correct, no,
scalar boson, yes.
Okay.
So, hello. So, as it has been said, this is an experimental overview of what happened to discover the scalar boson, which, as you know, was qualified as a giant. Its discovery has been qualified, sorry. It will be much better probably. I put it there because okay, it's better? Yeah. So, its discovery has been qualified as a giant leap for science, what is true, or the breakthrough of the 2012 year. But actually, the purpose of the talk today is to see what was necessary before this euphoric day of July the 4th, 3 years ago, to bring us to this discovery. So the topics of this lecture is actually to describe the main tools that have been necessary to the scalar boson discovery. Those tools start from the LHC machine, the experiments, the two generic experiments whose goal was the discovery, the particle signature in those two detectors, and finally we will talk about the main Higgs decay channels, which have been used to make the discovery, and also the passport of the scalar boson. As you know now, at the end of round 2, we have been able, with the accumulated statistics, to give information about the couplings and the properties of the boson. And of course, I will give you some results from both experiments, but more from Atlas because I am a member of this collaboration. So, very few things on the theory side, because I mean you have experts here that are going to present you the background of the scalar boson. So everything started in '64 by all those gentlemen, Brute, Englert, Higgs, but also Kibble, Hagen, and Guralnik, who introduced a scalar field with an important property that has non-zero vacuum expectation after the temperature becomes greater than a critical one. It is worth to notice that actually all those gentlemen were working on outside the electroweak theory for stronger interactions at that time, and their problem was to make vanish the Goldstone bosons that are also present in this field. So what happens is this famous plot here that after you have a field that after some critical temperature becomes as a value in the vacuum that is not a zero, right? And you can define this vacuum expectation. You can find that it's of the order of 246 GeV. So the implications of this model for the electroweak interactions was that actually all fundamental particles that at the beginning appears in the Lagrangian with zero mass, when the scalar field appears through their interaction, they acquire a mass, while gluons and photons remain massless, and you have the electroweak intermediate bosons, W and Z, that become KV. So in the 70s, this mechanism has been included in the standard model, what was constructed by Glashow, Weinberg, and Salam. And the Higgs mass in this model remains unknown. It's not it's a parameter, it's a free parameter. So in '73, there were some important discoveries from the experimental side, like the discovery of the neutral currents at CERN by the Gargamel detector, and this was the first indication that this model is exact. And in '76, there were some phenomenological already reviews on analysis of Higgs decays. And it is now a joke, but apparently the first phenomenological work on those, on the decay modes of the Higgs, whereby Ellis, Marike Gaillard, and Dimitris Nanopoulos, who did an important work defining the different channels. But as the mass was unknown in the model, they finally finished their paper by saying that for those reasons, we do not want to encourage big experimental searches for the Higgs boson, but we do feel that people performing experiments vulnerable to Higgs boson should know how it may turn out. So nobody was believing that actually this thing is possible to be discovered. In '83, finally, the discovery of the W and the Z bosons at CERN was the first indirect proof of the mechanism, right? Because they have been found at the right predicted masses. So, the Large Hadron Collider at CERN, you know all CERN. I have very few things to say. That it has been founded in '54 in order to build up again the scientific European community at the exit of the Second War. And today we have 21 member states that are the states that finance CERN. You have 6 observers, other states, 42 collaborating states, 17 contact states, and a series of major discoveries have been done at CERN, like the discovery of the neutral currents, the discovery of W and Z bosons, the search and measurement of the direct CP violation in the current system. The number of lepton families have been constrained to be 3 at LEP. The prediction of the top mass through the very precise measurements on an electroweak process. The evidence and the study of the quark-gluon plasma. This is another experiment at CERN. Creation of anti-hydrogen in the lab. This was the first time it was produced in the world. And finally, the scalar boson. And we have almost 10,000 scientists working in the site. The LHC genesis was a long arrow in the time. It started 35 years ago when people started to think about the future of the CERN. Then in '84 there was the first European brainstorming in the committee, the ECFA committee, to build up a proton collider inside the LEP tunnel. In '92 we had the first letters of interest of the experiments for LHC and the feasibility machines and the feasibility studies for the machine. In '94, the CERN Council approved the LHC construction, but actually in 2 steps because of financial problems at the time. So in '95, Japan, who is not a member of CERN, decided to become observer and approved the financial contribution. And this is a picture where you saw Llewellyn Smith, which was the director of CERN at the time, with the Japanese representative. Congratulate each other for the agreement, and giving a Daruma doll. A Daruma doll is a doll, Japanese tradition, where if you can see, there is only one eye in the doll, and the second, the one eye is to say that something is starting, the collaboration, and the second eye, I guess that by now is also painted, yes. So in '96 was a great year because in February CMS and Atlas experiments have been approved. On March, India and Russia announced also financial support to LHC. In December, Canada contributed to LHC, and the cooperation protocol with US has been also signed off. So, and thanks to all those contributions of members of states that were not member states of CERN, that the Council have approved the LHC construction in a single step. This was an important milestone. Here, I have to remind you that actually there was another accelerator in the States with a very short life, SSC. This was the American project that was foreseen to construct a tunnel 87 kilometers long and to achieve 20 TeV per beam. This has been started in '83. The construction began in Texas, close to Dallas actually, and the tunnel has been started to be excavated. Construction of magnets have been started, and the buildings in place, and also a lot of physicists have been hired at the time in order to run the experiments and the accelerator. That finally, as often in the States, in '93 the US Senate decided to abandon the subject, the project, and this was a disaster for the community, the American community of course, but a shock also for the scientific community around the world. And all involved American physicists start to think about joining European project, and this is why the States also decided to help financially the LHC project. So, the LHC is not a single ring, it's actually a series of rings at CERN. The life of a proton that will finally circulate in LHC starts in a bottle of hydrogen, which is ionized. It's in this place here, and the protons are sent first to a LINAC, which is here, and then to a booster, and then to the proton synchrotron, and then to SPS, and finally to LHC. And I don't know if you can see here, but each accelerator accelerates more and more the protons till to achieve the wanted speed within the LHC. And when you go from SPS to LHC, you have two injections in the two opposite sides in order to fill the two beams. So the LHC is made of this ring of 27 kilometers that was existing because the lab took place there. It's underground, 100 meters. And within this ring, you can find the radio frequency cavities, which accelerate each proton beam in the wanted speed. And these cavities ensure also the high concentration of protons within benches, not only the acceleration, but also the dimensions. You have also almost 10,000 magnets. This is the masterpieces of LHC. You have the 1,200 dipole superconducting magnets, quadrupoles that are foreseen to keep tight the dimensions of the beams, and you have higher order multiples because you need to correct imperfections in specific places. And you have also the insertion magnets in order to fill the LHC from protons coming from the SPS, sorry. So the whole ring is actually made of 8 octants, and each sector as a set of all those magnets, each sector is furnished and powered separately. So these dipoles have been the result of a lot of research and development. You can see them there, 2 dipoles. They are 50 meters long, and they operate in the temperature the lowest existing in the universe, right? 1.9 is lower than the vacuum in the space. In order to be able to flow the necessary current to produce the 8 Tesla of magnetic field without thermal loss. So it's superconducting magnet, and here you can see a slice where you see actually the 2 pipes that are where the 2 beams are circulating in opposite directions. This is iron that is filling the space in order to keep the system stable, because between the 2 superconducting magnets here, you have enormous forces that are developing. And here you have the two pipes where the helium is circulating. So what are made of those superconducting magnets? You see here, they are made by cables of niobium titanium alloy. That is an alloy that is superconducting, becomes superconducting at 10 degrees Kelvin. And each cable is made out of very small, very thin strands of those filaments that are all made by this alloy. So all magnets have been trained in specific holes at CERN in order to verify that can reach the necessary field. And they also fully tested for tightness, mechanical and electrical integrity, the different instruments that have to follow their stability and the field quality. And until the point where the tunnel was ready to be for those magnets to be installed, they have been stored in the fields around CERN. And if you have been around at this period, you could have seen such a picture where you see in the parkings actually of CERN the hundreds of magnets waiting for installation. So in LHC you have also the biggest space filter with nothing, with vacuum actually. You have three separated vacuum systems. You have first, you can see here again the same slice of the magnets. You have first an insulation vacuum for the helium distribution that is filling 15 kilometers of piping. And then you have the insulation vacuum which is necessary actually to isolate the environment from the cryomagnet, where you have the very low cryogenic temperature. And finally, you have the very ultra high vacuum that is filling the beam pipes, 48 kilometers, and that is with a very low pressure, as you see. So how we cool down the different LHC sectors? Actually, around the LHC tunnel, you have 5 cryogenic islands, you see here, and each sector has its own cryogenic plants with installation, you can see, distributing actually 10 kilotons of liquid nitrogen in order to cool down the helium to 80 degrees of Kelvin. This is the first step. And then you have to go even lower in order to bring the helium from 80 to 4.5 Kelvin. This is done using specific turbines. And when the helium is at 4.5 Kelvin, you can inject it in the cold masses of LHC. And at that temperature, the magnetic coils become superconducting. And finally, then you have to bring it down to 1.9 Kelvin, where it becomes superfluid. This is a particular state of the helium where the niobium titanium cables actually develop their best capacity to keep high currents without any thermal friction. So when we cool down for first time the LHC sectors, this of course went slowly, and it took some time. You see for each sector, as a function of the time, how the cooling down was developing. At the first trial it was a little bit longer, but finally one sector is cooled down during a month. We have a very strict monitoring system, of course, in order to follow the cryogenic stability. And here you see, for a sector that is 3.3 kilometers, all the temperature of each magnet and you see that all are at 1.9 degree of Kelvin. And this, of course, now we are used to see, but at the beginning it was fluctuating because a lot of issues have happened. So building up the LHC, it was a titanic achievement. It was a prototype machine. But of course, as all those colossal constructions, it went through several bad surprises, delays for financial or for technical origin, failures, accidents, and you will see a few examples of those issues in some of the next slides. So where I am, okay. So, as we said, within the tunnel we have several dipoles, and there is interconnections between the different dipoles. Here you can see an interconnection. In the interconnection you have to connect the beam pipes, you have to connect the filling of the helium, the cryogenics, the electricity, everything. All this is a very delicate place, and this is where actually the most of the issues the engineers encountered were in this place. So the first was the below crisis and repair, and this happened also there. What is the below? The belows are placed between the interconnection of the beam pipe from one magnet to the other magnet. Actually, when you cool down or you warm up the accelerator, there is a thermal shrink or expansion, right? And in order not to break the tube, there is a kind of below that ensures the electrical contact between the two pieces. And here actually what happened, this is the famous object that is placed there. What happened is that some of those fingers have been found to enter within the beam tube. This was, of course, a cause for losing the beam. So people had to identify the places within the 27 kilometers where this problem happened, and then to repair it. And in order to identify the places, they developed a specific tool that is like a tennis ball with a detecting instrument inside. The ball has been inserted in the beam tube by compressed air, detected all the places where the fingers were entering in the tube, and then the people went there, opened the tube and repaired. This was 2007. But the biggest accident was in the 2008, you probably remember, after the beginning, the first filling of the LHC, people were increasing little by little the beam energy, and finally, in the 19th of September, it was the dark day, a violent warm-up happened in some interconnections. The superconducting status failed. We had an enormous amount of energy that flew in the magnets, an explosion that caused a lot of damages along quite a long range. So this, of course, has been investigated, has been found to be due to a bad interconnection between the cables, the superconducting cables coming from one magnet and the other magnet. Here in this place, normally the two cables are glued one to the other, and finally they found that actually there were places with no glue, with empty space, and empty space is resistant, right? Cannot conduct the current. So what happened was that actually we warm up the sectors. Of course, no beam for 18 months. First of all the necessary studies to understand what happened there. 39 dipoles and 14 quadrupoles have been repaired or exchanged because the damages were extremely severe. And the experts consolidated all these places, all those interconnections have been studied and consolidated. And also they installed additional safety procedures because actually the explosion should not happen, right, if everything was really controlled.
But in the end it was human mistake?
Sorry?
In the end it was human mistake?
Not really.
Somebody was fired for this? Or
No. What happened is actually that this thing here has to be constructed with more safety. And if you discuss with the experts, they can, if they know you, they will tell you actually that here what it should be done from the beginning, that is done now, is that they have to build special pieces that keep this glued region quite safely. And this, at that time, because of financial restrictions, wasn't done correctly. And so this is the reason why it was a collective, if you want, mistake, right? Imposed by restrictions. But of course, people wouldn't think at that time that such an accident could arise. Otherwise, you see, it's not a single person mistake. So, okay, a few numbers for the LHC. So it takes 4 minutes to fill one beam with 1,000, with the number of bunches of protons in 2012. Each bunch contains 10 to the 11th protons. And this bunch has dimensions that actually vary along the LHC ring. Why they vary? Because we wanted to adapt the instantaneous luminosity of the beam along the ring, and having actually the highest possible one at the interaction points where we have the experiments. So what is the instantaneous luminosity? Is a function of the number of protons per bunch you have, times the number of bunches, times the turns of the beam per second, divided by something that is describing the dimensions of the bunch. And here you can see this small drawing here, where you see the interaction point, before the interaction point and after the interaction point. And you see that before and after, actually, you have dimensions of beams that are larger, because there you don't need to have an increase in a large instantaneous luminosity. So your beam is a little bit larger, and you have specific optics there which squeeze down the bunches in order to have the maximum probability for collision at the interaction point. So here you can see how during a period of a week, for instance, you have the fillings of the SPF, of the LHC with protons. You see that at the beginning of each fill, you have a lot of interactions, and during the time, this number of interactions decreases because the quality of the beam decreases. And you have then to stop the beam and then restart a new fill, etc. So, of course, in order to have as much as possible data, you have to optimize the lifetime of the beam. And in order to have the longest possible lifetime, you have several parameters that you have to control. The first one is the collimation of the beams. Without a clean beam, you can have immediate magnet quench. If you have particles that are hitting the different magnets, you lose the superconducting status of the magnet, and the beam is lost. We have almost 100 collimators along the LHC, and this worked extremely well during the first run, during the last 2 years. And all people is very happy, nothing happened unexpected, and the beam from this point of view was quite controlled. You have several other points that can challenge the beam lifetime. You have this so-called electron cloud within the LHC. Now you can ask what electrons are doing within the proton collider. Actually, in the beam pipes, you can still have electrons that are loosely controlled and in the material of the beam pipe. And some electrons are ionized and enter in the beam. They interact with the protons, and this gives rise to an electron cloud that interacts with the other the consecutive packets, and this creates a situation, a kind of cloud within the beam pipe that can create instabilities. You decrease the emittance, the beam size, and then the lifetime can be shortened. So the engineers developed some cure methods in order to clean up the beam from this electron cloud by injecting some kind of high intensity, low energy beam that actually cleans up the walls of the beam pipe, and the improvement we observed was really impressive. So there are other effects that can they can shorten the beam lifetime. We observed some single event effects that actually is related to radiation from the beam that can hit the different electronic equipments that control the beam and cause beam losses. And the solution was, let's say, easy. People went down and they moved or shielded the sensitive material in order to decrease this rate, and really they improved it by a lot. The second effect is what is called UFO, which is unidentified falling object. Probably it's related to dust particles that people identified mainly close to the main injection points in the accelerator. And in this case, there is something which looks like this. This is a picture taken with specific cameras, and the beam can. There is something falling within the beam, it traverses the beam, and the beam is lost within a millisecond. So we speak about losing the LHC beams. This, of course, has to be controlled because you have an enormous amount, colossal amount of energy that is released immediately. So the experts develop methods to dump the beams in specific cases where the beam quality has been deteriorated and you want to stop the beam and fill again the accelerator with a new beam. And or when the beam monitors around the accelerator detect some activity that becomes quite dangerous, let's say. And in this case, you have specific magnets there along the ring that kicks off the beam along a long tunnel which is under the Jura. And at the end of the Jura, you have an enormous amount of concrete where the beam is dumped. And the beam, before it's dumped, is actually diluted by specific magnets in order not be concentrated, because if it is concentrated, even the concrete will be melted. Okay. And so here you see how the beam from a single spot is diluted like an E when it is going to the dump. So this is for dumping the
Question: how does the beam cross the vacuum? I mean, how do you?
Oh no, it's you have a pipe which is foreseen only for the beam to get to this specific tunnel towards the beam dump.
Yeah.
You have another vacuum.
You have another vacuum.
Yes, you swap the beam, but there are specific valves that opened the second.
But it has to be very quick. I mean, how do you?
Yes.
Yes.
Yeah. The dump is taking place in 1 millisecond. So, after 2 years of functioning, the lessons from the operation is that it was a huge technological achievement, actually. It was a prototype machine, and in very short time, actually, the experts demonstrated very high capability for prompt reactions. All those problems, the issues they have encountered, they analyzed them extremely fastly, and they designed the adequate solutions, let's say, to overcome the problems. In some cases, they achieved beam that is even higher in than the designed values. We went even beyond the expectations for this first period of LHC running. And we also in development of performance monitoring and complex control tools at all levels, not only the beam dump, but the control of everything. And so here you can see how the expectations were in terms of total integrated luminosity, starting from the green curve is for 2010. Here there is multiplied by 100 the luminosity we had in the first period, which was just after the restarting. The red curve is for 2011, where we accumulated 6 femtobarns, and finally, during the same period of time, from April to November each year, how fast we accumulated in 2010 the 23 femtobarns. So the secret of all this is that the excellence of expert and technical teams working at LHC, they are really the very few people expert of the world capable to make it work as such a huge project and solve the problems that arrive and that are completely new. And here you see the teams that have been working during the 18 months of stop after the run 1 to consolidate actually the different problems that happened in the first phase in order to be able to increase the energy to 7 TB per beam. And here you can read, if you want later, the different tasks of consolidation that took place during the stop. So since few weeks, we experience now round 2. All magnets are trained at 7 TB, working properly at 7 TB, but the working energy for this year will be only 6.5 TB per beam. The acquired experience was of great help, actually. However, there are some worries because we wanted to increase the instantaneous luminosity by a factor of 2. That means double the number of bunches circulating in the LHC. And this means that actually we will have bunches that are spaced by only 25 nanoseconds instead of 50 nanoseconds, as it was in the 2 previous years. And this implies some warnings about possible beam-beam interactions that can create instabilities, and electron cloud, the famous electron cloud issues, and also one might expect higher rate of those falling objects that can stop the beam. So this is so far for the LHC, the accelerator. Now we swap to detectors that allow us to take pictures of the Higgs. So, as you know, when you have high energy collisions, the observing particles that emerging from there can be electrons, photons, muons, taus, tops, everything. And we have to construct detectors able to trigger on all those particles, reconstruct and identify them. So, LHC's prime goal was the scalar boson, there we got it, and is still some beyond the standard model discovery, the SUSY. All those subjects imply candles that are, again, all those particles we presented here, electrons, muons, etc., and missing energy also. So the problem is that LHC energies, the parton density is very, very high, and on top of all those interesting candles, we have a huge background that can bother us from observing the interesting signals. So the detectors we have to construct must not only identify precisely and efficiently the signatures we want to study, but also to distinguish and discriminate the background. So those two conditions are the main ones we have to take into account and keep in mind. So the constraints for the LHC detector was first to be hermetic. Hermetic means to see the particles, to measure the particles, to be sensitive in 4 pi if possible. And here you see the two generic detectors that are Atlas and CMS, and they go down, then they have active detectors down to very small angles, below 2-3 degrees, along the collision axis, right? The second point is to be stable with the time. Since we know that we have to stand longer run periods, all those detectors are also imbricated, and even if you can go down during the out of beam period, it's very difficult to have access inside. So the detectors have to be stable along 2, 3, 4 years. To be hard, of course, as possible to the radiations. Here you see a diagram which shows the amount of radiation you can have in your detectors as a function of the radius. This is the Z, the collision axis, and you see that you can go up to thousands of grays, especially in the forward regions. So your detectors have to stand the radiation, have to be radiation hard. Also to stand the very high rates, because you want to survive to very high luminosities in order to have a lot of statistics. So starting from 40 megahertz, you cannot record all the events. You have to record only the interesting ones. So you have to have triggers that are capable to distinguish and to the interesting signatures, and to decrease the initial rate down to something you can write on tape. And finally, all your interesting physics you want to measure populate an energy spectrum that goes from very huge EV to possibly a TV. So you need to be able to identify all particles in a very large spectrum. And of course, as we said, to have a very high power or rejecting background you don't want to measure. So, as you probably know, the particles going through matter react in different ways. Charged particles interact with atoms and kicking out electrons. So this signature is used to reconstruct the charged trajectory. And for this reason, we use for the charged particles a magnetic field in order to be able to reconstruct the particle momenta. The neutral electromagnetic particles interact with matter through Bremsstrahlung, or creation, or pair creation, and the energy is released till full absorption in the calorimeter, and we can measure it. The muons are interacting very little with the matter, and we measure them by using a magnetic field. You see here a usual picture that shows you, here is the CMS detector. This is again a slice. Here is the interaction point, and you see that actually the different particles do not leave the same signature within the detector. The charged particles are bent in the center, because of the magnetic field, and they let the energy, if they are electromagnetic, in the electromagnetic calorimeter, and then you have the hadronic particles that are interacting in the hadronic calorimeter, and then the blue track, which is a muon, that actually interacts very little in the first detectors, and they are measured here, which is the magnetic spectrometer. So the calorimeters for the Higgs have been discussed a lot of time because during the design of the detectors, because it was actually the main R&D for the LHC detectors, because actually even at that time, the region, even if the Higgs mass was not known, the very low mass, it was privileged by the SUSY prediction and also the electroweak fits. Here you see the theoretical prediction for the cross-section times branching ratio of the Higgs as a function of its mass. And you see that actually as the Higgs interacts with the heaviest possible particles, if the Higgs was very, very heavy, you would have only the electroweak bosons in which it could decay, right? If it is very light, you have all possible decay channels, and this low energy, low mass region is a quite difficult one, actually. And this was privileged by SUSY, and knowing that this region is difficult because you have B's, taus, etc., in which the Higgs can decay, it was thought at the time that the most challenging but realistic decay to find the Higgs was the Higgs to gamma gamma, to 2 photons, which you can see here. It's a small branching ratio, but it's a clean signature. So the calorimeters for the Higgs discovery has been based on the discovery of the Higgs to gamma gamma. What we should do in order to be able to reconstruct the diphoton final state. And for this, since the Higgs at low masses has a natural width that is meaningless, few MeV, this means that at low Higgs mass, the resolution you can observe is just determined by your detector. For this reason, you can see it here, on top of very large background, if you have a medium, let's say, resolution detector, a resonance will appear like this, while a very good detector will give you easier to detect, to identify result, right? So, from this point of view, the CMS collaboration chosen to construct the calorimeter, the electromagnetic calorimeter from crystals that have a very nice resolution, and they can be read by photodiodes, sorry. So the calorimeter is looking like this. This is a drawing. You have several crystals, you can see here, with different geometries depending on their place in the detector. And they have a very good resolution, actually, at small energies, at 2.4%. That is an excellent resolution. Why they chosen these lead tungstate crystals? Because they are quite dense, actually. I don't know if you know the radiation lengths. A material is determined by its radiation length, that is actually the distance after what an electron loses 1/e of its energy. So if your material has a short radiation length, it means that you need a shorter distance in order to absorb a given energy. And this was very good for the lead tungstate. And the same for in transverse, it was also very dense. The problem was with that material of lead tungstate that is a little bit dependent on temperature, so you need to stabilize the temperature in which your detector is. It has an excellent resolution, as we said, but it's very sensitive to radiation, and this is what we suffer in LHC environment. So for this, they have developed a system of laser monitoring that follows degradation of response. Here you see as a function of the date within the year, how the response of a crystal was decreasing because of radiation. And the decrease is is more important as you go in forward regions where the radiation, as we saw, becomes important. So they have this system of laser monitoring that can follow the degradation and correct after the response, and you obtain something which is flat. The Atlas calorimeter, it was completely different approach. It's a calorimeter that is within a cryostat because it uses as active medium liquid argon, and it has also lead absorbers. The advantages of this calorimeter is that it's stable, it is radiation hard, and is fast and uniform. You see here, before it goes, of course, in the bath of the argon, liquid argon, the absorbers. And actually, it's also another property that is the readout electrode is in longitudinal direction, contains 3 layers that allows to make for a single particle measurements in 3 different depths. And this is, it gives you a very good possibility to reconstruct the direction of your particle. This calorimeter has a resolution that is less good than the CMS one, but it remains very good for the physics that we want to do. It's 10% instead of 2.5% in the case of CMS. For muons, the 2 detectors, Atlas and CMS, chosen different approaches. CMS has a solenoid superconducting magnet with a 4 Tesla field, that is an enormous field, and you can see here the solenoid, and this, the field is then returned in those red yolk that are interleaved by chambers that are measuring the different particle trajectories. While in the Atlas, you have 2 fields actually, a solenoidal one, and the toroidal one that is made for all the 8 toroids, that is made especially for measuring the muons. 1 hour.
1 hour now. You decide what you want to do.
It's 1 hour
1
now.
hour now, yes.
Okay. It's okay? We can continue. You need a few minutes of talk.
I think
We can continue. Okay.
if you can.
Okay, I have to accelerate. It's good to tell me that it's 1 hour. So here is the magnetic fields of Atlas CMS. Here you see a slice. And you see that in CMS, a muon track, for instance, is bent in this direction in phi.